I mentioned that what we wanted was to get cosmic rays up to energies of 10 to the 20 or 10 to the 21 electron volts. I showed how to do it with Fermi acceleration, so stochastic acceleration through crossing a shock front many, many times and getting some kick every time you do. But I didn't say really what is the maximum energy we can reach. And what are the problems in actually reaching very high energies and the limitations. So let's do that first, and then I'll leave the sources for a little bit and talk about propagating cosmic rays to the Earth, and then about neutrinos, and then about detecting some stuff at the Earth. And that should put us at the very end. Okay, so first thing I want to talk about is the maximum cosmic ray energy. And by that I mean the maximum energy we can reach by accelerating cosmic rays in the processes we saw last week. So, last lecture. So last time we talked from the first order Fermi acceleration, we found that the gain in energy of one particle crossing many times on average is, it's proportional to the shock velocity that it's crossing times a factor of 4/3. And that means that when you cross one time and your initial particle energy is zero, then once you cross, on average, you will have an energy that is 4/3 V shock larger than you had it originally. Okay, so let's put some numbers here. For a supernova remnant, a young supernova remnant, which is, I believe I mentioned it before, the leftover bubble of matter that is expanding outwards from a supernova that happened some thousands of years before. And that might be one of the shock fronts that we're talking about that the proton could cross to get accelerated. We have, let's say, an initial energy of 1 GeV for a particle that is crossing the shock. And this is a shock front that is moving outwards with a velocity of some 10% of the speed of light. Those are typical velocities for newborn or young supernova remnants, and then they actually can go down. How many crossings do you think it would take to get to an energy of 1 PeV? If you can do it in your head, it's amazing. Okay. It turns out it's about 100 crossings. So the calculation you want to do is you want to say 1 PeV is 1 GeV multiplied by this factor some number of times. And that number of times turns out for these particular values is about 100. And that is a problem, because every time you cross, you lose some of the particles that leak out of the acceleration region. So if you need 100 shock front crossings to get to the energies you want, then the number of particles after 100 crossings has gone down by this factor. This is the number of initial number of particles. This is the probability that the particle exists in the region, stays in the region, after it crosses the shock front once. And this is a number, because the probability, this is a number that is below 0.1, And then if you multiply that many times, then this is a very aggressive reduction in the number of particles that remain once you do these crossings many times. So that means that even though in principle these acceleration mechanisms can get us to the energies that we would like, it takes a long time. And then we need to think whether the particle can actually stay in that region for that long. I mean, we see that the probability that it emerges out of the region is non-negligible. And so that leads us to think about what is the maximum energy that we can reach. And for that, let's talk about, you probably remember this from your EM classes, Faraday's law. Now the curl of an electric field is this. Okay, right? So very roughly, what this translates to, if we want to not do derivatives, is that the magnitude of the electric field divided by the size of the region in which the acceleration is happening has to be roughly the magnitude of the magnetic field divided by the typical time scales associated to that region. And remember, this u is the speed with which the shock is moving outwards from the center of the region with respect to the matter that is around it. Okay, so then we can use this to estimate what the maximum energy is. And to do that, let me actually write the equation and you'll realize what it means. This is the maximum energy of the particle. So no longer magnetic field, but energy. Charge of the particle. I'm going to do a line integral that is over the region surrounding, over the line surrounding the acceleration region of the electric field. Don't get confused, this is energy, this is electric field. Sorry about using E twice. And if you do this and use the relations we just wrote, this is this quantity. So I just plugged in this in here. Okay, so we put some numbers to get our feeling for the magnitudes. This is 1 PeV, 10 to the 6 GeV, times the charge of the particle, times magnetic field in micro Gauss, times the speed of the shock over 10% of the speed of light, times the the size of the acceleration region. And I'm putting typical numbers here, 10% of the speed of light, 10 parsecs, for something that has astrophysical origins. So again, if we do this for a young supernova remnant, let's plug in some numbers. B is indeed about micro Gauss near the shock front where the acceleration is happening in a supernova remnant. Let me write this U slightly, actually it's consistent. It's 3% of the speed of light. Again, this is velocity measured with respect to the surrounding matter of the shock. And the region itself has a size of 0.03 C, so U, times 1,000 years, which is what we call a young supernova remnant. So this is how big the region is after 1,000 years of expanding with that speed. And this is about 9.2 parsecs. 1 parsec is about 3 light years. You're going to see, for some reason, astrophysicists like to mix CGS units with SI units with something else, and they typically measure quantities that should be in parsecs or kiloparsecs in centimeters. No idea why. So if you plug in these numbers, then it turns out that you can reach energies of roughly 300 TeV times the charge. And remember, 1 TeV is 10 to the 12 electron volts. So you are reaching roughly energies of 10 to the 14 electron volts. The reasoning behind this becomes a bit more clear if we frame the problem from a different perspective. And that leads us to what we call the Hillas criterion. And we're going to write eventually the same equation, but coming from a different angle. This is, before going into that, maybe let me comment a bit more about this. So 300 TeV times Z puts us roughly in the PeV range. And then you might have heard the word pevatron mentioned before. Pevatron is a source of particles of PeV energies, in this particular case, cosmic rays of PeV energies. So the reason, and we see PeV scale cosmic rays in the flux of cosmic rays that we detect, but we don't know where they're coming from, as I said in the past lecture. The reason why we believe that at least up to energies of 1 PeV or so, these could be made in supernova remnants comes from here. So from the fact that given typical values for the parameters of such objects, you naturally can get to energies of the sort that you want in order to explain the galactic cosmic ray flux. That doesn't mean that those are the sources, it means that in principle they're capable of. In practice, there is no confirmation of that as of yet. Okay, so Gilles criterion. This is a slightly different way of framing that. So what this is expressing really is that the acceleration of a particle inside the acceleration region can only last while the particle is inside the region. And that means that the condition to reach the maximum energy means that the Larmor radius or the gyro radius of the particle has to be at most equal to the size of the region, because when it's bigger, then it will just leave. Remember, a particle moving in a magnetic field is bent with some curvature that is given by this. If the curvature is bigger than the size in which the particle needs to be contained, then that particle is no longer inside the region. So it no longer can be accelerated. If you plug in these numbers, it turns out that, this is a horrible B. And let's call this, you're going to see, actually I call this U. You're going to see these transformations appear here. And I'll explain that in a moment. So E max is the same, nearly the same as I wrote before. Okay. Let me explain where these come from again. So if you remember from last lecture, we had a region that is moving outwards with some relativistic outflow, with some speed or Lorentz factor rather gamma, and then inside there's a shock, and the shock is the one that is moving with a velocity u with respect to that outflow, and the distance from the central emitter, so the center of the supernova remnant in this case, from where the particles were originally emitted, to the shock front, that is roughly the size of the acceleration region. That's what this is saying. So you have an equation now that looks like this. It's the same dependencies. I'm not plugging in the numbers again. But now you know where it's coming from. It's coming from demanding this. And that is a necessary condition for a source to be able to accelerate particles up to some desired maximum energy, but it's not sufficient. It doesn't mean that it will do it. In fact, typically since we don't know much about particle acceleration at these energies, typically we plug in an extra fudge factor here, which we call the acceleration efficiency. It's a number between 0 and 1, and it can be anywhere between 1% and 100%, depends on what we think is reasonable. So together with the Gilles criterion that I just wrote, by the way, this is, let's use this. This is Gilles 1984. So not that, I was going to say not very long ago, but now I think maybe I should not say that. Okay. So together with that, now we can make a plot that allows us to map in terms of magnetic field and size where the different candidate sources of cosmic rays could be for some required maximum energy that we are interested in. So let me plot here the size of the source, and this is the comoving size. So gamma times r, and this is centimeter. And then here I'm going to write the magnetic field strength. Strength. So this is And I'm going to write this in Gauss. Okay, so let me see. So this is going to really span many orders of magnitude. Over here, it's like 10 to the 4. Again, now you see here centimeters, and I'm going to go from 10 to the 4 to 10 to the 25, at which point it doesn't make sense to talk about centimeters anymore. But that's how it is. So this is 10, 16, 22. Okay. We're jumping around a lot in orders of magnitude. This is 10 to the minus 10 Gauss. This is roughly 10 to the 14 Gauss. And let's see, 12, what is it? 8, I'm just going to try to write the ones that matter here. Minus 4, 2, okay. You want the exact values, go to that paper, you will see it much better than I can draw them here. But then let's think we have protons that we want to accelerate up to 10 to the 20 electron volts. So that's what I'm demanding. And that will impose conditions on the size times the magnetic field, which is how that product enters in the definition of Emax. And for a proton, it turns out that that means that anything that is on that line will satisfy the condition of reaching 10 to the 20 electron volts according to the Hillas criterion. This is for one particular choice of the u velocity. So here I wrote 1. So this is traveling at the speed of light with respect to the surrounding medium. If I had demanded something a bit slower for the shock velocity, then that shifts the line of Emax up. So this is for 0.01. And if I had, instead of use protons, iron, and iron has 26 protons, then this will shift, according to the definition, the lines down by a factor of the differences in the z. So for protons, that will put us here or here, depending on the choice of the velocity. So this is iron, and these here are protons. And now you start to realize, before I had been talking only about protons, but I had mentioned that it's also nuclei that are in the flux. Now I'm going to start slowly introducing nuclei in the mix. So what this allows us to do then is, let me actually make one extra mark here. This is 1 megaparsec. This is 10 to the 10. So roughly about here is 1 astronomical unit of the distance from the Earth to the Sun. This is roughly 1 parsec, and this is roughly 1 kiloparsec. So just to get your bearings, if you're not very familiar with these units, the closest star, Proxima Centauri, is 4 parsecs away from us. The size of the Milky Way is about 30, the diameter is about 30 kiloparsecs. The Sun, from the distance from us to the center of the galaxy, is about 8 kiloparsecs. And the distance to the Andromeda galaxy, the closest galaxy to us, is about 1 megaparsec. So that's what that means. Okay, so now our astronomer friends actually have models and measurements of different sources and their sizes and their magnetic fields inside that they can infer. And that allows us then to start putting blobs of possible candidate sources on this plot. So this is a neutron star. I should say neutron stars, because it's the population of stars that's making the size of the blob. This is, over here, gamma ray bursts. And gamma ray bursts, I will say more about this later, but they are the very short flashes of gamma rays emitted by especially luminous supernovae. And this over here is active galactic nuclei. which is galaxies with active supermassive black holes. By active, I mean they are accreting matter. And so they are shining typically in X-rays or radio or gamma rays. Okay, so what the plot is telling us is that more compact accelerators, so smaller r, need higher magnetic fields in order to keep the particles trapped in that smaller region. Conversely, bigger accelerators can get away with having a weaker magnetic field. But it really doesn't give us detailed information. It's just for us to map the possibilities out in a nice two-dimensional space. Still, it's a tool that we use even today as mainly to get our bearings right. Okay, so this is as much as I want to say about particle acceleration. And then let me jump into particle propagation. So remember that plot that I drew at the beginning where we had the production, propagation, detection? We're going to jump into the middle now, the propagation. And when doing so, I will focus mainly on the higher energies, so 10 to the 17 electron volts and above of cosmic rays. And the lower energies have interesting dynamics themselves, but I'm going to skip it because we won't have time to finish it. But if you're interested in that and propagation of cosmic rays from the Milky Way, we can talk afterwards. Okay, so let's talk about ultra high energy cosmic ray propagation. But before going there, I want to ask if there are any extant questions. Okay, good. Then, yes. So the question, the question is where are the yellow blobs coming from, and they come from observations of these kinds of objects. So astronomical observations. So from astronomical observations, we can infer the size of the neutron stars and the magnetic field that they can subtend, and so we can just overlay those ranges on top of the lines that we had already drawn. Yeah. Well, what this is telling, yeah, okay, that's a good point. So what this is telling us is that, let's focus on protons for a moment. So these are the white lines, and you know you need to be at least on that line if you want to get to 10 to the 20 electron volts, or higher if you want, or above the line if you want to go to higher energies. When you draw the yellow blobs on top, what this particular one is saying, for instance, is that neutron stars, at least some part of the population, have the necessary combination of R and B to be on that line or above it. So in principle, they have the conditions to accelerate particles, protons, to 10 to the 20 electron volts. But they don't have the conditions to accelerate, for instance, let's see, I should draw another line here. If you want to go to 10 to the 25 electron volts, that will put you here. And then you are no longer able to do it with neutron stars. By the way, 10 to the 25 electron volts is not an energy that any of these things could ever reach. So I'm just exaggerating. Yeah. Okay. Is there any other question? Cool. Okay. So let's talk about cosmic ray, ultra high energy cosmic ray propagation. And remember, the propagation here is over cosmological distances. So I'm talking about tens of megaparsecs up to few gigaparsecs, and the size of the observable universe is 10 or so gigaparsecs. So really we're traversing the whole thing. Okay, so why, let's start from the beginning. So the Larmor radius that we had written over there, it also tells us that at energies above 10 to the 17 electron volts or so, these cosmic rays cannot be made in the galaxy because they would have escaped. So if we use that Hillas criterion over there, let me write it in this way. I'm going to use now not Emax, but rather the definition of the Larmor radius, which I'm going to now put some numbers on. It's like 33 kilometers, This is the energy of the particle that is being held inside a region, is charged, and as usual, the size of the magnetic field. And this is, in more useful units, this is about like 3 times, actually, let me put it this way. 1 kilometer, just so you get a better view of this, 1 kilometer is roughly 3 times 10 to the minus 14 parsecs. So that means that 33 kilometers is roughly 10 to the minus 12 parsecs in more useful units for us. Okay, so if we want to plot the size of the Larmor radius in parsecs as a function of the energy of the particle that is being accelerated, so cosmic ray energy, and I'm going to write it in GeV, then, let's put some numbers, sorry, 10 to the 5, 10 to the 11 over here. So let's see, 6, 7, 8, 9, 10. 10 to the 8, 10 to the 9, 10 to the 10. And over here we're going to have something that goes from 10 to the 5 down to roughly 10 to the minus 2 parsecs. So minus 1, 0, 1, 2, 3, 4. But more or less that works. 10 to the 1, 1, 10, 100. Okay, there we go. If we plot now that for protons, the Larmor radius for protons as a function of energy, then that will put us roughly along this line. If we do that for iron, which is Z of 26, as I said before, that puts us along this line. This should be parallel, sorry if it doesn't look like that. But what matters here is the following. This, let's see if I can actually draw it properly. There we go. This is more or less the diameter of the Milky Way. So this should be about 30 kiloparsecs. That's the diameter of the Milky Way. And for the purpose of what I'm saying right now, the Milky Way is a disk. With some width of roughly 400 parsecs and a diameter of what I just said, like 30 kiloparsecs. Yeah, and we are somewhere close to the edge. So that's the diameter of the Milky Way here, and this is the, oh, yeah, we're fine. And this is the Milky Way disk height. Okay, what is it telling us? It's telling us that if we want to reach the highest energies, then the Larmor radius of those particles will mean that those particles cannot be contained inside the galaxy. So even if we had accelerators that are able to reach 10 to the 20 electron volts or so inside the Milky Way and emitted cosmic rays with those energies, those cosmic rays won't stay in the galaxy. They will have leaked out. So we will not be able to see them, except maybe a few stragglers. And that means that whatever cosmic rays of energy above 10 to the 9 or 10 to the 8, depending on where you make the cut, depending on the masses of the particles involved, on the Z of the particles involved, they need to be coming from outside the Milky Way. Possibly from objects like have the same dynamics like I wrote over here. So something that's being accelerated by first order Fermi acceleration. So that's the logic behind cosmic rays at the highest energies not being from the galaxy. They cannot be confined magnetically by it. Very well. So then they need to be coming from outside, and that means that we need to solve a propagation equation. So let's keep things independent of source modeling. So I don't care about exactly what happens inside the sources, and I don't even care about the identity of the sources. As I said before, they could be essentially anything that is compact enough and able to accelerate particles up to very, very high energies. And the compactness comes from the fact that we need to obtain a pretty high magnetic field, and the conditions of the Hillas criterion get satisfied. Okay, so let's write the propagation equation. And for that, we start by writing the co-moving. I think you had some cosmology lectures in the past couple of weeks, right? Okay, hopefully you did. So the co-moving number, density, and for the sake of what I'm going to say next, I'm going to assume that this is purely protons. Okay, the logic is similar when there's extra nuclei, and this means GeV per cubic centimeter. So number of particles per unit energy per unit volume. And I'm going to call that Y. It's a function of the energy of the protons. We'll see that it's a function of redshift as well. Remember, these are particles in my initial sketch that have redshifts up to 4 or so up to tens of gigaparsecs, depending on where you stop. And the co-moving number density of not just protons, but any particle, is the scale factor to the power of 3 multiplied by the real number density. Okay, so the number, maybe let me be explicit about this. This is the scale factor. This is 1 over 1 plus z. There we go. Okay, so the propagation equation is really, if you have seen diffusion equations before or Boltzmann equations before, it is just that. So what I'm going to do is write an equation that will allow us to propagate protons while the protons lose energy because the universe is expanding while they propagate, and also because they interact with photons along the way. And that is an equation on dy dp. I'm going to say what each thing means in a moment. This is the Hubble parameter. This is just the energy. I'm going to draw the P in EP for a while. This term will represent energy losses due to pair production of the protons on the CMB along the way. This represents the different kinds of losses due to proton-photon interactions. Now they're inelastic energy losses. And this is injection of cosmic rays. So let me explain this one by one. This one here is the losses due to the adiabatic cosmological expansion. So just to the fact that the energy that we see at Earth of any particle is a factor of 1 plus z smaller than its original energy at production, because it has traveled some distance in between, and while traveling, the universe has been expanding. Okay? And that applies not just to protons, it applies to photons and to neutrinos as well, as we'll see later. Then you see these B terms over here. Both of them mean the same fundamental thing. These are the energy loss rates of the protons along the way due to different processes. And I'll come to what the processes are in a moment. So B is just shorthand for dE dt. Okay, that's, let me make it with a minus sign, so the EDT is positive and minus that is negative. Okay, so then you see two terms, and the first term will be due to this energy losses due to pair production, and by that I mean P plus gamma, and I'll talk about what gamma is, where gamma is coming from in a while. Go to E plus plus E minus. So the final state proton is lower energy than the initial proton. And this one is energy losses due to what we call photohadronic interactions or photopion interactions. I'm going to write this photopion. And that means P plus gamma goes to stuff that does not include a proton anymore. So to first order. And that means you're losing protons here. You're piling down protons to lower energy here. I'll expand on this in a while, but then first let me give you the big picture. And this final term is the injection of protons by sources that exist at a different redshift. So this is a function of energy as well and of redshift. So this last term, this L here, that's where all the astrophysical modeling comes in. That's where you can propose a particular population of cosmic ray sources and then build a geometry for how these cosmic rays could be expanded, and then say there are so many sources at this redshift and so many at this other redshift. We'll come back to that later, but I won't go into the detail of modeling specific kinds of sources. This all applies for protons. If I were to do this also for heavier nuclei, so we saw all the way up to iron, then there's one extra term that I won't include because it becomes a bit complicated, and that is called photodisintegration. Not included. Photodisintegration. Disintegration. And that happens when a heavy nuclei interacts with a photon along the way, and it gets broken down into a lighter nuclei plus stuff, including photons and whatnot. So that means that if you start with an iron nucleus at the beginning, when you inject them from the sources into the stream of cosmic rays that will become eventually what we see at the Earth, those iron nuclei will not necessarily reach the Earth as iron, but will cascade down as a result of this process repeatedly occurring. So you will get from iron to nitrogen to helium eventually, and maybe to protons. Okay, so I will not include that. And the final thing, actually that's not the final thing, so the next thing that I want to do is recast that equation into something a bit more useful for us. The physics is the same, but in the propagation of cosmic rays, it doesn't really help us to have a derivative over time. It's more useful to have a derivative over redshift. So for that, I'm going to use our knowledge of cosmology, and I'm going to use this relation, which you are probably familiar with. Okay, and then this is h, is the same h that I wrote there, so let me now write it here in full. This is the Hubble parameter calculated at some redshift, and for the purpose of everything that I'm going to say, we're living in a lambda CDM universe. Okay, so when I show pictures of how these fluxes of cosmic rays look at the Earth after propagating everything, assume that I have plugged in the values of the concordance model into the density parameters and the Hubble constant. Okay. Even if you change those values by a little bit, the results don't change by a lot in terms of how much it affects the flux. So if we use this, then we can recast the equation. And it looks fairly similar to what we had before, but just for completeness, let me write it here. So we're going to have a factor of 1 plus z in the denominator, and the rest actually proceeds as before. So let me write it in full so you see the dependence of all the parameters. So this depends on hz. This is ez. This is easy. So you see that the difficulty here in solving these kind of equations is that they are in redshift and in energy. And that means that for every redshift step, we need to solve it across a spectrum of energies if we want to get the total information of the energies of the Earth. Okay, so what we will do is we will evolve that equation from a high value of, initial value of redshift. So I'm gonna say maybe Z max of 4 all the way down to a Z of 0, where we are. And the result of doing that will be the flux of protons that reaches the Earth after being affected by all these effects over there and after being injected more and more across different redshifts by sources. I want to stop here for a little pause, but before that, is there any question? Have you seen equations like that before? Okay, I don't see any hands, so I'm guessing no. Okay, let's stop here, and then we actually dive into that equation before and see how the cosmic rays look at the Earth. Let's give us a... So what I want to do now is pick apart each one of these terms just a little bit. I won't go into full details. And at the end, I will show you what the solution of that equation looks like numerically. And in one of the exercise problems, you can do it by hand in a simplified situation. Okay, so let's go in steps. Let's start with the last term, the cosmic ray injection by the sources. CR injection. That's the easiest one. Let's assume that there's a population of cosmic ray sources. Those are those cosmic particle accelerators. All of them are identical to each other. They're just lying at different redshifts. So some of them are closer, some of them are farther away. And each one of them injects or emits protons with the same spectrum. So each cosmic ray source emits, this is let me write it first. This is the number of, okay, I'm just gonna write it and I'll show you exactly what it means. Okay. The units of this is GeV, inverse GeV per second. So it's the energy, number of particles per GeV per second emitted by a source. Remember, Fermi acceleration gives us a power law in the energy of the protons, and there's a maximum energy. So to account for the fact that at some point you run out of steam, so you reach the maximum power that your accelerator can reach in terms of energies, we write it as an exponential that will become important once the energy of the particle is close to what the maximum is that the cosmic ray source can give you. So that's an exponentially damped power law. That's what it's called. Okay, that's the first part. And then we need to know how many of these sources are at different redshifts. And that is hard if you don't know what the sources are. So we can only make kind of guesses, informed guesses. So number density of cosmic ray sources. This is now in units of volume. So per cubic megaparsec. I am going to write it as, let me write it as this, h cosmic ray as a function of z. And then it will become apparent what that means in a moment. So it's easier to explain if I draw it. So this is redshift, and this is 0 to 6, 1, 2, 3, 4, 5. And what I'm going to write here is this quantity HZR of Z. And what this is something that is proportional to the number of cosmic ray sources as a function of redshift. And by proportional, I mean I have normalized it in such a way that the number is 1 at some low value of redshift, or rather 0 at some low value of redshift, and then it grows from there. How do astronomers or astrophysicists actually measure those kind of number densities? They actually count things. So they make surveys of different candidate sources. They measure the number of active galactic nuclei or the number of supernovae, etc. And they can also separately measure the redshift at which each one of these measurements is being made. And so they can count the number of sources that exist at each redshift. And in particular, one very generic measure of how much matter there is at each redshift is called the star formation rate. The star formation rate is a quantity that tells you how many stars are being formed at each redshift. And this is found by counting how many supernovae happen at different redshifts. Every time a supernova happens, lore is that in that region there will be matter being formed in the sense of structure being grown. So when you count the number of supernovae, you are indirectly counting the number of future structures that will be formed at that redshift, and that is a function of redshift that we will use to parameterize our number density of cosmic ray sources. So we're not going to say that a cosmic ray source is a particular kind of object, but we're going to say that the number of them traces the amount of matter that exists at different redshifts. That's the logic. So that function over there, if we assume this is star formation rate, it looks like something that, I forgot to put here, that will peak at redshift of 1. Then it will go down like this. And what this is saying is something you probably already know. Star formation in the universe peaked way, way, way before our time. That is what this is saying. Sometimes we consider modifications of this star formation rate if we look at specific source kinds. For instance, gamma ray bursts, those very intense flashes of light that I talked about earlier, that come from especially luminous supernova. That has a similar structure, but it turns out that there was a second period later when they also peaked. So this is the number density of GRBs, gamma ray burst, and this is the number density that would follow the star formation rate, conventionally the star formation rate. And this is, again, now we're talking about like gigaparsec scale distances when we're at redshift of 1. Okay, so we have each source emitting the same kind of cosmic ray spectrum. We have how the number density of sources evolve with redshift. We can put this together and then write the last term in that equation, the injection term. And that will be something that looks like this. It should be like this, 1 plus z times this. Okay, so this is just the number of cosmic rays injected per unit energy, time, and volume at a specific redshift. And one key thing here is that if I'm evaluating that at an energy of E and a redshift of Z, then I need to plug in here the energy that is been redshifted up to that particular value of Z. That's why there's an E times 1 plus Z on the right hand side. Okay. And that leads me to the second part. Actually, let me write it here at the very bottom, because it will be just a small thing. The adiabatic cosmological expansion, that speaks to the first term there. And that is just an expression of what I said earlier. So the energy at, just for the sake of clarity, at detection, so at the Earth, this is the energy at production times, divided by 1 plus z, due to the fact that as the particles propagate, the universe is expanding. Okay, so that takes care of this term over here, the first one. And what I just said takes care of the last one. So we need to deal with the in-between terms, which are the ones that are parameterizing the interactions of the protons with the cosmological photon fields, like the CMB. And those are the interesting terms, because those actually modify not just how many protons you get at the Earth, but also what the distribution of their energies is. Okay, so interactions with cosmological photons. Okay, so for this, there's two important cosmological photon backgrounds. They're isotropic and diffuse. The first one is the one I've been mentioning, and that is the CMB. So let me write this in log scale, log 10 of the energy in GeV. And this is number density of photons at redshift of 0, so the local universe, and this will be in cubic centimeters, inverse cubic centimeters. For the CMB, let me see if I can get the scales right. This is like minus 20, this is like minus 6. This should be like minus 12. Apologies that I don't draw every tick, but that is beyond my artistic capacities. This is 1, this is 100, and this is 1,000. Okay, for the CMB, this is a black body spectrum, as you know. So it looks, let me see, kind of like this in log. And it has a peak at roughly 0.2 millielectron volts. Okay, that is not the only one though. That is not the only source of cosmological photons. In the local universe, this is about 411, as you know, CMB photons per cubic centimeter. I was looking into the discovery papers when preparing this lecture, and I found out that the title of the paper where Penzias and Wilson in 1965 reported the discovery of CMB is very inoffensive. It's called A Measurement of Excess Antenna Temperature at 480 MC per second. I don't know what MC is. That's it. They didn't say anything else. And it's 2 pages. It's an APJ in 1965. But in the same issue already, Dick, Peebles, Roll, and Wilkinson explained this as a possible remnant of the early universe. So they already identified a few pages before, actually it was a letter to the editor in 2 pages, that this was probably the CMB. So there you go. Okay, so for the CMB, this is, as I said, a black body spectrum. So I'm going to write it like this. Z of 0. So this is in the local universe. Actually, here, 1 over pi squared, epsilon squared. Boltzmann constant, minus 1. And this is about 0.23 millielectron volts, which corresponds to 2.73 kelvins. There are, as you are very aware, small variations in the temperature. They are completely ineffectual for the purpose of propagating protons or other particles. They are fundamental for cosmology, though, of course. Okay, so since the CMB was generated at a redshift of 1,100 or so, then afterwards it didn't receive any more injections of photons into the stream of CMB. And this is essentially a single burst of particles that were, of radiation, sorry, that was injected a very long time ago and then left to evolve. And because of that, then if you want to calculate the number density of CMB photons at a redshift z greater than 0, then it's like this. Let me write it first and then I'll explain why you will see a weird power here. CMB. Okay. E over 1 plus z, z of 0. Okay, so what I'm doing here is scaling the number density per unit energy per unit time. That's why you see a power of 2. And if you're familiar with cosmology and you're thinking that this is just, sorry, now it's correct. If you're thinking this was just the number density without this, then this power would be wrong. Okay, so we know how to evolve it. It's pretty easy. But that's not the only photon background, as I said. There's another background that comes from the fact that stars across redshifts emit in the UV and optical, and that the stars are often surrounded by dust, and the dust absorbs that optical and UV and re-emits it as infrared. So that is what we call, or what astrophysicists call, the extragalactic background light. And it looks rather like this. So the peak, the first peak here at high redshifts, that is the UV optical, and the low peak is the re-emitted infrared. There's fewer photons from that EBL than for CMB, and that will have an impact on what their importance is when propagating protons. It is also more difficult to model the redshift evolution of the number density of EBL photons. Okay. So the reason is these, as you can imagine, are emitted over many redshifts because we have stars not just at the one time, but distributed over distances. And that means that you need to solve an evolution equation in order to find what the number density is of those photons at the local universe or at any redshift. And that becomes complicated because we don't have direct access to what the injection spectrum is of those photons. And so we cannot really solve this equation with assurance. But let me just write it how it looks like. So the number density of EBL photons at a particular redshift will be at the same factor, and it will be the integral of the injection of photons. This is just the Hubble factors here. The injection of photons at higher redshifts. And again, I need to redshift this. So what this is saying is there is, like in the case of the protons, some population of sources that are, in this case stars, that are injecting photons, the EBL photons, and with some distribution of the number density over redshift. And if you want to find out what the number of those photons is at a certain redshift, then you need to account for the fact that at redshifts higher than that, there were already sources emitting those photons, and the ones you see at redshift z have been accumulated all the way from z greater than that value. So z max of 4 or so. There's many ways to get to estimate this, and it involves making kind of informed guesses about what the number density evolution of the sources of the EBL photons are. So let me skip that because that is actually where the astrophysics comes in. But this is how it looks at redshift of 0. And we can use some informed say considerations about this to find how it looks at different redshifts. And that's what I have done in the numerical results that I will show you in a little bit. Okay, so now we have two sources of photons, and those will be the ones that the protons will be interacting with. Let's talk about pair production first, and then we'll talk about inelastic proton-photon interactions second. Oops, I left it there. Okay, so this is an old business actually. I was looking at when the first pair production cross sections were calculated, and it was 1930 something, and they have been, of course, improved since then in terms of how easy it is to calculate it, but the result is, of course, the same. So for those of you that like Feynman diagrams, okay, so this is I think it's probably the lowest order Feynman diagram that I want to take care of here. And the initial calculations were done by Blumenthal in 1970. Sorry, no, this is the refined calculations. The initial calculations were done in the form that we're going to see today. Gluck, Stern, and Hull in 1953. Back when there was only one physical review. This is physical review 90, 1030. And in fact, this is physical review D1, and then some page number. Okay, so the calculation happens in two frames of reference. There's the lab frame, and in the lab frame, it looks like this. You have a proton that is incoming. It collides with also an incoming photon, and then they make an angle theta between them. This has initial energy E. And then in the rest frame of the proton, then it looks like this. So we have the proton here. There's an incoming photons of energy E epsilon prime. Out come the two electrons, the positron and the electron that we are interested in. So I'm going to call it E plus and E minus. And there are some angles here, phi plus, phi minus, prime. Okay. Energy of the positron is this, energy of the electron is this. So there is an isotropic photon distribution in the lab frame, but when you put it in the rest frame, the electrons are going to be emitted in a region that is confined to be roughly 1 over the gamma factor of the system, right? And that in the direction of the incoming photon. So if you then let me just sketch the calculation. I'm not going to do through the whole thing. But if you want to write the energy of the photon in the rest frame of the proton, P, then that looks like this. 1 plus beta cos theta. And then the beta it's the usual thing. Okay. And I'm going to consider that this is much bigger than 1. So it's really a relativistic situation. So the threshold for particle production, for pair production, is the one you imagine. So you need your photon to have at least twice the mass of the electron to create them at rest, if that's an equality. And we need also a cross-section for the interaction. And the cross-section is something that, if you are so inclined, you can look up. That's the one I was saying was calculated originally in 1934. It's just QED, so you can actually calculate it. So I'm just going to write what it depends on. So in our coordinate system is the cosine of the two angles, the outgoing angle of the positron and of the electron. And if you want to look it up, it's a lengthy calculation. This is, so look at the people that actually work on this, Bethe and Heidler. This is 1934. And the other one is Raka in 1934 as well. Okay, for now, just believe me, there's a way to write it. What matters for us is how you calculate the rate of energy losses using that. And energy losses of the protons. Okay, so there's some simplifications you can make. The cross-section is invariant to changes between the plus and minus sign of the angles, and that introduces a factor of 2 and simplifies the problem. So once you do the full thing, it can be written as the energy loss rate of the proton can be written as this: 2 times the threshold energy all the way up. You need to integrate over the energy of the photon, then the energy of one of the particles. I'm choosing the electron here, and then the angle of one of the particles. Again, it has to be the same one, so it's the electron. And then there is this factor, I'm going to write it in a moment, and the cross-section. It's after I have integrated over one of the angles. As I said, the problem is symmetric, so you can do this. Okay, so this parameter here is just shorthand for, let me write it exactly, for this, minus the momentum of the electron, okay, for this. And if you see the Blumenthal paper over there, you can see that these can actually be simplified massively and get an expression that is a lot easier to deal with. Okay, so that's the energy loss rate of protons interacting with the photons. And the way it looks for us becomes more apparent if we now look at the typical scales. So let me write again log 10 of the proton energy in GeV. This will go from 8 to 13, so very high energies. And here what I'm going to write is the energy loss length, not the rate. And the length is L, this. I wrote it in megaparsecs, okay. So remember B is this in our equation in the central blackboard. The first thing here that we can draw is axis 10 to the minus 2, 10 to the 7 parsecs. This is minus 1, 0, 1, 10, 2, 3, 4, 5. Okay, I did it wrong. Let me see if I can correct it. Okay, minus 1, 0, 1, 2, 3, 4, 5, 6, and that's as best as it will go. So 10 to the minus 1, 1, 10 squared, cubed, 4, 5, 6. Okay. The first thing we can draw here is this, the adiabatic energy loss term. And then I'll put in the one we just calculated. And that is roughly here, between 10 to the 3 and 10 to the 4. This is, of course, independent of energy. So this is adiabatic losses. This is just I'm going to word it like this. The energy loss process here is the inverse of the Hubble constant, parameter, sorry. And this is 1 plus z to minus 3.2. 3 over 2, sorry. So this is just a line. The energy loss rate is a constant over time. Over energy, sorry. This is calculated, by the way, at redshift of 0, local universe. Okay, and then the one I just wrote here, sorry, the energy loss rate for per production of protons on the CMB first. It looks like this. Let me see. 10, 9, 10, 11, very badly drawn. 10, 11, 12. So 10, 11 here, okay. So this is now E plus, E minus on the CMB. Okay, what is this saying? This is the energy loss rate. So the fastest energy loss process wins at any energy. And that means that at low energies, at least in the picture that I've drawn over here, at low energies, it will be the adiabatic energy losses that dominates the energy loss terms in the equation. And then at some point, then it becomes the CMB, the one that dominates. And it's dominated at a certain energy because the energy of the spectrum of the CMB photons has a peak. So it is more efficient at some energy range than in others. And if you instead now use the EBL, so the extragalactic background light, it looks like this. So now this is E plus, E minus on the EBL. It is always or nearly always above the CMB energy loss rate for per production. And that means that it's nowhere as efficient as the CMB to take energy away from the protons, and that is because there's fewer EBL photons than there are CMB photons. Okay, so there's one extra term here, which is the proton-photon inelastic interaction rate. Let me quickly at least diagram it because I want to draw it there as well. And then we'll stop there. So far, we have only been dealing with the loss of energy of the protons due to pair production, but the proton remains in the flow of cosmic rays, just with lower energies. But now let's look at inelastic energy losses, the ones that make the protons disappear. And I call this initially photopion interactions, also called photohadronic interactions in general. And that should harken back to what I said at the very, very beginning, the first lecture. So you have proton plus photon interactions will give you typically a delta resonance. I'm going to skip that part. But eventually the delta resonance will decay into this. The charged pion will decay into a nu mu plus an antimuon, which decays further. And then the neutron itself, the beta decays. Okay. Some other times, what happens here, as I said at the beginning, is you get pi zeros. So sometimes you actually do get a final state proton. But in principle, you are losing at least partially some of the protons you had initially. This should be pi zero. The pi zero decays into 2 gamma rays. Okay, so now you are at least partially disappearing some of the protons you had initially, especially when you're producing neutrinos. We'll come to neutrinos in the next lecture, but what I want to do now is calculate what the energy loss rate for the protons is via these processes. And this comes by computing what is the threshold energy that the protons and the photons must have in order for this process to occur, for us to generate a final state nucleon and a final state pion. Mass differences between neutrons and protons are small. The mass differences between pi zeros and pi pluses are small for the sake of the argument. So let's just be a bit sloppy about the calculation and just say that the center of mass energy that we need to trigger this process is, the kinematics is always the same. So it's 2 times the proton energy times the photon energy. And this needs to be larger than the mass of the particles you're producing. And if you plug in the numbers, look at one of the exercise problems, it turns out that this imposes this condition. This needs to be larger than about 0.16 GeV squared. Product of proton energy and photon energy needs to be about that quantity. And the quantity is fixed by the fact that you need to, just by the fact that you need to produce this. Okay, so for the CMB, I already erased it, but the photons are peaking at roughly 0.2 milli-electron volts. Remember, it's a black body spectrum. And that means if you want to satisfy that condition, that you need protons of energies of roughly above 10 to the 12 or so GeV. Okay. Very roughly. So if you account not just for the energy at the peak of the spectrum, but also for the fact that the spectrum has a width around the peak, then you can do a more involved calculation that tells you, including width of the CMB spectrum. It turns out that you can trigger the process pretty efficiently down to energies of roughly 5 times 10 to the 10 GeV. So protons with energies of 5 times 10 to the 10 GeV and above will undergo these processes. And this here is an important result. That is called the Greisen-Zatsepin-Kuzmin GCK limit, or cutoff. And this was found by Greisen in 1966 and by Zatsepin and Kuzmin also in 1966. And this means that if you have cosmic rays traveling for some distance of cosmological scale, then they will most likely undergo such an interaction and will disappear. So how long do they need to travel in order for that to happen? That's something we can very quickly estimate by computing the mean free path. The mean free path of a proton traveling and potentially interacting via that process is, let me not make the calculation, I'm just going to lay it out here. So this is an integral of the cross section for that process, which depends on the proton energy and the photon energy, the number density of photons of the CMB as a function of energy, of course. And then you need to integrate that over photon energies. And this is to be inverted because this is distance. And this is roughly about 30 megaparsecs. 30 megaparsecs, for the purpose of this, is the local universe. So the universe is, as I said, a few gigaparsecs in size. The causally connected universe, observable causally connected universe, is about a few gigaparsecs in size. 30 megaparsecs is next door. So the argument is, if we have very high energy cosmic rays emitted by some population of sources, and they are being emitted with an energy above this threshold value of 5 times 10 to the 9 GeV, the GCK limit, then it only takes about 30 megaparsecs before they will interact with that process and disappear. And that means that no photon, no cosmic ray above this energy will reach us from beyond 30 megaparsecs. Every single cosmic ray within tree level that we see with energies above that has to come from the very local universe. And that means then that that process is super efficient. And then we can draw what the energy loss rate associated to that is. And let me draw it properly. This, like this. On the CMB, this looks like this. So this is now photopion on the CMB. And on the EBL, this is just a lot higher than this. So what this is telling us is that at certain energies that are enough to trigger that process on threshold, then that will be the dominant energy loss process, photopion interaction. So if we want now to look at the full picture, then as I said, you need to always take what is the fastest energy loss process. So it will look like this at each one of the energies. And that determines how fast the energies are lost and how the energy spectrum of protons looks like at the Earth. So I know I'm already at my mark, but so let me just show you a few pictures and then I will stop, because otherwise I won't be able to show you what the end result of this whole thing is. So bear with me just a few minutes, maybe 4 minutes or so. So what we do is then we solve that, thank you, that numerical equation, that equation numerically. I think it's off still, the screen. Ah, okay. Now it's turning on. No, I think it turned off. Yeah. Because I heard the fan stopping. Maybe not. Okay. Okay, that's fine. Thank you. So what we do is you can solve this equation numerically. It's not possible really to do it by hand if you want to include every term. But if you want to look at the exercise sheet, there's one exercise where I turned everything off except the first term, and that you can solve by hand. So there are some observations of the cosmic ray flux at the Earth. These are all data points. I'm just showing them here because it will allow us to neatly see how the flux looks. Energy is in the x-axis. Flux of the cosmic rays that reaches the Earth is in the y-axis, multiplied by 3 powers of the energy to make the whole thing flatter, because otherwise it will be very inclined and more difficult to plot. And those are data points that I'm putting there, and I'm going to fit my predicted spectrum of the cosmic rays at the Earth. So after I solve this equation, at the very end, I'm going to find the flux of protons at z of 0, the density of protons at z of 0, and then with that, I'm going to find what the flux is of those protons, which is an easy transform. You multiply by the speed of light and divide by 4 pi to get the whole quantity per steradian. So what you see there is what typically is going on when we make fits to cosmic ray data. There are some data points from the HIRES experiment, which, as I said, is an old experiment. There's a prediction for what the flux could be at the Earth, given some input parameters for what each one of the sources injects, and how they're evolving in redshift. I'm assuming that they evolve as a star formation rate for what I'm going to show. And this is just a simple chi-squared fit with an extra pool term here that is representing the fact that these cosmic ray experiments don't really measure energies very well. So there's some uncertainty there. They can only measure it to within a factor of sigma e. That's what that term will do there. So we do that, and then for our baseline prediction, then we actually get something that can fit the observations. So it has 2 peaks. They are representing the peaks that come from the energy losses due to to pair production. That this value is representing the pair production losses, sorry. And then the highest energy is the result of this GCK cutoff that doesn't allow very, very high energy cosmic rays to reach the Earth. And if this is under certain assumptions, I'm assuming that the spectrum has e to the minus 2.5 dependence, and that I am putting by hand a very, very high maximum energy of 20.5. We can change parameters and see how it affects things. So if I increase now the maximum energy to which protons can be accelerated artificially by hand, then I go from the black line to the blue line, and that allows me to have more cosmic rays at the highest energies at the Earth. And conversely, if I decrease the maximum energy, it does the opposite. I'm killing off the flux at the highest energies. You can change how steep it is the energy spectrum with which you inject protons into the flow. And again, it will have certain effects, but you already see that if it is too far away from a value of about 2.5, which is our baseline in black here, then you start having issues about how to fit both the high energy points and the low energy points. So it has to be something roughly around 2.5 or so. And you can change also how the sources evolve with redshift. And for our baseline assumption of star formation rate in red, you see that things fit well, but if you change that for the more aggressive gamma ray burst evolution, which I showed earlier has a second peak at high redshifts, it doesn't change quite much. So there's some freedom there in how the source number density can change. Okay, so in reality, the measurements look like this, and it's a lot messier than what I just said. There's points all over the place. At the highest energies, we have, I think, 15 events above energies of 5 times 10 to the 19 or so post GCK cutoff. And that means that we can do very little statistically over there, but there's experiments today that are getting there and we're reaching more statistics. But overall, and this is the last thing I'll say, then what I showed is that we can model the propagation of cosmic rays. You need to include the interaction with the photon backgrounds, you need to include the adiabatic energy losses, and you need to know your astrophysics. But in the end, what you can do is actually explain the observations of cosmic ray experiments, and I will come back to that later in the next lecture. Thank you.